In this lecture, we'll be looking at the issue of parameter selection for autoregressive integrated moving average, or ARIMA processes. Let's remind ourselves first of an ARMA process. And the idea here, recall, was to combine autoregressive of order P and moving average of order Q processes to create a robust class of models to model stationary time series. So our ARMA definition, we have our white noise process of epsilons, and we say that our y's, these form an ARMA PQ process if for constant parameters, mu, thetas, and phis, we have the following defining equation. Recall the idea here is that today, if we think on a daily time scale, y differs from its mean with a piece of memory from how it differed from its mean yesterday, all the way back to a piece of how it differed from its mean p days ago. Effective new information with a new white noise term, and then we get a piece of memory of yesterday's noise term, all the way back to a piece of memory, the noise term from Q days ago. And again, we note for certain conditions on these parameters, we will have an ARMA process being a stationary time series. But many time series are not stationary, and so we move to ARIMA models. So you see we add a new parameter D, and we have an I here for autoregressive integrated moving average. And we say a time series YT is an ARIMA PDQ process if you difference it D times, and the resulting time series is an ARMA PQ process. So the idea here is that we were taking a non-stationary time series Y, we difference it D times to achieve stationarity, and that new differenced time series we then can model as an ARMA process. We can then back things up, recall that differencing or differentiating a time series. Inverse process to that is the integration of a time series. So we can then integrate this time series xt d times to get a model for our original non-stationary time series yt. And the question that we have is, how do we choose the parameters d, p, and q? Note, d is the number of times that we will difference our original time series. P is the number of memory parameters for the autoregressive portion, and Q is the number of memory parameters for the moving average portion. And the general rule that we will follow, is we do D first. So the first thing we will address in addressing D is the issue of stationarity. Typically, you're seeing D be in the interval, in the set 0, 1, 2. So typically, we are differencing our original time series 0, 1, or 2 times. And the standard approach to do this is to look at the autocorrelation structure. So the idea here will be that we're given time series data. So we have y0, y1, up to yn. So we have n terms in our data set of our time series for y. And we construct the sample autocorrelation functions for the original time series, if necessary, the first difference, then if necessary, the second difference of yt. And we look for evidence of stationarity. And if we see our sample autocorrelation function decaying to 0 slowly, this is going to be evidence of non-stationarity. So we look for a sample autocorrelation function that decays to 0 fairly quickly. And the idea is we want to choose the smallest value of D such that the D differenced YT time series appears that it could be stationary. We want to do this in this minimal way because it's important to not over difference. So strange things can happen if you over difference, and in terms of autocorrelation structure. And in general, you really want to do it as few times as possible, because remember, we are going to then integrate our time series to get a model for our original time series. So we would integrate the differenced time series that's being modeled as an ARIMA. After we choose D, then we move to P and Q. To give an example with some real data, if we look at crude oil, this is crude oil data for April 2019 to April 2020, and we see here in the left-hand plot, we have the log price of crude oil, and in the right-hand plot, we have the log return. Now remember, we know that the log return, we usually denote this as RT, and the log price, we usually denote as little pt. And we know that the log return is the first difference of the log price. So we saw this example in a previous lecture, right? Our log price differenced would be this time series here, pt minus 1. But if capital P is the price, the actual price, then we know from our properties of logs, this is the natural log of pt over pt minus 1. And we see we have a confirmation here that right, this on the right is the definition of RT. So we're confirming that the log return is actually the first difference of the log price. And so we see that reflected here. Now note this is a little bit, we see a pretty big regime switch here. This, when we see here the data starting in March of 2020, we see things being much more volatile because of the beginning of the coronavirus, the COVID-19 pandemic. But we see here again, this is a time series, and this is its first difference. And if we look at the autocorrelation structure, we see something very different. So we know, first of all, that generally these types of prices, log prices, are not stationary. And we can see that reflected in this sample autocorrelation function for the log price. We see it decaying to 0 very slowly. So all the way out to 11 lags, we still have autocorrelation above 0.8, which we expect. Then when we look at the sample autocorrelation function for the log return, we see it decays to 0 fairly quickly. So at by lag 3, we're below a correlation that's in absolute value smaller than 20%. By lag 4, we're close to 0. We get some strange larger behavior over here, likely due to the fact that this pandemic data is being picked up in this date range. But nonetheless, this decayed to 0 range quickly here makes it more reasonable that we can choose D equal to 1. Now keep in mind, we don't need autocorrelation to drop to 0. One of the points of using ARIMA and ARIMA models is to actually have some kind of autocorrelation structure. And what we have here for these first several lags looks quite reasonable for something to be, for a process that's modeled as an ARIMA. So in this case, we would set D equal to 1, and we would be looking at modeling the log returns as an ARIMA PQ. P and Q still to be determined, but because RT was the first difference of the log prices, our log prices, we would claim, are being modeled as an ARIMA P1Q. So specifically, we are differencing our log price time series one time, which results in the log return time series, and modeling that as an ARMA. Once we determine what our D will be, we then move to selecting the parameters P and Q. And again, that's for the ARMA in particular. We have the P for the autoregressive part and the Q for the moving average part. And this is typically done via the procedure of maximum likelihood estimation. So we deferred to a separate lecture to cover maximum likelihood estimation, but we look at how that is set up in this particular instance. So first, all bold letters here will represent vectors. So bold Y represents the vector of time series data. So this is your data that you're given. And then we have mu, a theta vector of the parameters for the moving average portion, and a phi vector, the phi parameters for the autoregressive part. So this is what we have set up for our ARMA process. And so the idea here is our ARMA process, we have already differenced. So Y is the result of an already differenced process that we believe is stationary. We let f of y, given the parameters, be the density of y. So by definition, that depends on those parameters. The likelihood function, we flip the perspective. So the likelihood function is a function of the parameters of the model. So it's a function of thetas, phis, and mu, but the sample data, our y vector, is fixed and given. So our likelihood function is defined, and we should have a mu in here. The likelihood function is defined as that density evaluated at this given data vector y, given these parameters. And the idea is L of theta phi mu represents the likelihood of the sample under the model where our density function for y is using these different parameters. So it's these parameters that we will now tinker with in the maximum likelihood estimation process. And so the maximum likelihood estimator of our parameter values is the value of, well, it's the value of these parameters that maximizes the likelihood function. So you can think of it as we're going to compress just for, so we'll have our theta vector, our phi vector, and mu. So imagine we're compressing this higher dimensional space into a line, and then above it here we'll have the density. We want to pick, so the density evaluated at our vector y, given those parameters. And we want to move around these parameters to maximize the likelihood or the value of the density function at when this y is plugged in. So the key thing to think of with maximum likelihood estimation is it's actually all of the parameters for that density that are in play, that are our independent variables. The value of this, the set of parameters that maximizes that likelihood, we denote by, we put hats over the variables to denote that they're estimators, and we put a subscript of ML for maximum likelihood. Now, it's often the case that we actually don't maximize the likelihood, but rather the log likelihood. And note that because the natural log is strictly increasing, maximizing this strictly increasing transformation of our objective. Sure, it will result in a different maximal value, but the maximizers will be the same. So maximizing the likelihood or maximizing the log of the likelihood results in the same vector of maximum likelihood estimates for the parameters. And a key thing here is if you assume that your elements of your y vector are sampled independently, then you have the property that the joint density is the product of the univariate densities, and that works out nicely mathematically in terms of maximization. And again, I refer you to the maximum likelihood estimation lecture, which is done separately for that. Once you have this estimate for the maximum likelihood estimators, we then have some standard criteria that's used to determine the values of P and Q. So the AIC is one set criteria for choice of P and Q, and it's defined in the following way. So the AIC is defined as -2 times the log likelihood, and the log likelihood evaluated at the maximum likelihood estimators. So this L sub MLE is the maximized value of the log likelihood function, plus 2 times P plus Q. So the idea here is we want to minimize this AIC, and let's think about what that does. First, this is a sum. So to minimize this AIC criteria means we minimize the first term and we minimize the second term. Minimizing the first term, we have -2 times the log likelihood. If we're minimizing the negative of the log likelihood, that's the same as maximizing the log likelihood. That means we are trying to minimize this first term to get a good fit. So minimizing this first term is maximizing the log likelihood, and that means, right, the higher the log likelihood, the more likely our observed data is. The second term, we have 2 times P plus Q. We want to minimize that. That means we want to have P plus Q be as small as possible, which means we want to penalize having a large number of parameters. Remember what P is. P is the number of time periods the autoregressive features look back in time. Q is the number of time periods that the moving average features look back in time. So by minimizing P plus Q, we're trying to minimize P, we're trying to minimize Q. We're trying to choose as few look-back periods as possible. And the idea here is we're trading off between these two. So this first term, minimizing it, is a goodness of fit procedure. Or you could say it's minimizing this first term is pressure to get a goodness of fit satisfied. So a good fit, the actual observed data is likely under the model, and minimizing the second term is trying to choose as few parameters as possible. And so we have this trade-off. And the idea, one word that's often used for this is the idea of parsimony. So we don't want to have an overfit, right? We want to have enough of a fit that our model is actually capturing what happened. But we don't want to use a ton of parameters because we don't want to be overfitting, having a model that's overfitting the data. And so the minimization of the AIC is building in a trade-off between minimize this term for goodness of fit, minimize this term for fewer parameters in the model. Another standard criteria for fitting these types of models is the BIC, or the Schwarz's Bayesian information criteria. This is defined per this equation here. You see the first term is the same as in the AIC, and the second term is very similar to the second term in the AIC. Notice AIC had a 2 here instead of a natural log n. So again, the first term is the log likelihood evaluated at the maximum likelihood estimators for our parameters. So minimizing that term, again, is a goodness of fit. The lower this first term, the more likely our observed data is under the model. And the second term, again, we are minimizing the number of parameters, but note that you have ln of n here. And so n, of course, is the size of your sample. So the larger your sample, the heavier the penalty on the number of parameters here. So the same trade-off between goodness of fit and use of few parameters, we just have a more substantial penalty on the number of parameters here, because this penalty increases in size with the size of your sample. So putting the AIC and the BIC next to one another here, we can see the difference explicitly, and we know that natural log of n once we get to natural log of 8, or rather, once we get to 8, natural log n is larger than 2. So once your sample size gets to 8 or more, your BIC is penalizing P plus Q more than AIC. And as a result, AIC will usually choose more parameters than the BIC, just because the penalty for parameters in BIC is more severe. These are two very commonly used criteria for parameter choice. And you'll see that this is done, actually, the AIC and the BIC come up in many different contexts outside of just working with ARIMA models. But this is how you can set your parameter estimates for P and Q. So to sum up, first you determine how many times you have to difference your time series to achieve something that you believe is stationary, or is likely that you have evidence that it's stationary. Once you have that, you can use maximum likelihood estimation to create your AIC and your BIC criteria and minimize those. And that will help you determine the most appropriate values of P and Q for your ARIMA model.